All right, let me just talk about, when we have acids in water, let's take a look at another example here. We'll do H2SO4, AQ. And so H2SO4 in water, it's going to hydrolyze water. Actually, H2SO4 is an acid, and the water is amphoteric, so water can go either way. So we have H2SO4 and water. This is an acid-base reaction. It just so happens that water is the strongest base present. Right? So normally we don't think of it as any base, but since water is here, we're going to have hydrolysis. So this is going to give us H3O plus HSO4 minus. And so let's say I have a 0.10 molar H2SO4. There are two types of problems that you're going to encounter. One type of problem is just to calculate the pH. If we just need to calculate the pH, we can shortcut it because, as we see, when we do stepwise, in the stepwise procedure, each successive step typically leads to less and less hydronium for acid solutions. And so we probably can stop at the first step, but that's not always the case. Sometimes we have to continue on beyond the first step. And so let's take a look, and we can turn this on here. Take a look at this first step here. The Ka for this, you should know. What is the Ka value for this acid? So look at Appendix D, we'll see on the Ka chart sulfuric acid, they just write strong acid, which means that the K is going to be, you notice H2SO4 is a strong acid, therefore the Ka is, what do we say? Very large. And so the Ka equals very large. And so what we do with very large is we just assume there's complete reaction. So we'll just start off with no reaction initially. Here and here. And then there's going to be a change. The change is going to be complete, so we know what X is going to be. X is going to be the whole thing. So this is going to be minus 0.10 plus 0.10 molar plus 0.10 molar. And so at equilibrium, we should have no sulfuric acid molecules left over, and all of them should be hydrolyzed into hydronium ions and hydrogen sulfate ions, like this. All right, so normally in a typical question, if I was asking for pH, in a normal, like 90% of the problems, you'd just stop here, because if we look at all the other contributors are going to be minor compared to the first step. However, for sulfuric acid, that's not the case here. Because in step one, this is going to be the major. The major is, okay, what are all the hydronium ion contributors? We have Ka1, we have Ka2, and we have Kw. And so typically we think, okay, Ka1, that being the largest, very large, is going to be the major contributor. Then that for sure is the case. If we look at Ka2, what is Ka2 for sulfuric acid? Ka2 for sulfuric acid is the Ka for HSO4 minus, which is 1.1 times 10 minus 2. Now, if you think about 1.1 times 10 minus 2, is that on the larger side or is that on the smaller side of Ka? Ignoring the strong acids, is that on the larger or the smaller? In fact, the ones with the numerical value, what was the biggest one that we saw in Appendix D? Do you recall? Actually, did we scan this table yesterday? No? All right, let's take a little scan of the table. Let's see. And we're just going to look at the magnitude of 10 to the minus 5, 10 to the minus 12, 10 to the minus 10. look for the biggest and the smallest. So 10 to the minus 12 is smallest so far. Let's go over here, 10 to the minus 12, 10 to the minus 10, 10 to the minus 13. Ten to the minus 7, 10 to the minus 2, 10 to the minus 2, that's kind of big. There, as far as 10 to the minus 12. So 10 to the minus 13 so far is a small, oh, here's a 10 to the minus 19. 10 to the minus 19, that's extremely small. This is significant. What's significant about 10 to the minus 19?
You can make the simplifying assumption.
I'm sorry?
You can make the simplifying
You can make the simplifying assumption, but there's something else that's significant about 10 to the minus 19. There's something else that's significant about 10 to the minus 19 is KW. What is KW in reference?
It's larger.
Yeah, KW is larger. KW is 10 to the minus 14. So far, all these are stronger than water. But when we hit this one, this is actually weaker than water. So water should be a bigger producer of hydronium than HS minus. And so when we do this, when we do steps, we just go from the biggest to the smallest. So if I was dealing with HS minus, I would do water, KW, before the Ka2 for H2S or Ka for HS minus. So 10 to the minus 19 so far is the smallest. The biggest one is going to be here. This is the biggest one, it looks like, 0.3 or 10 to the minus 1. Do you see that? 0.3 or 10 to the minus 1. And so this gives us some reference points for the numbers. And so typically we'd stop here unless step 2 would be a significant contributor. Now, when would step 2 be a significant contributor hydronium in terms of pH? Well, it's when the K is fairly large. So if we look at step 2 here, that's, the second hydrogen, the second proton on sulfuric acid comes off to form hydronium and sulfate here. And so this would be Ka2 for sulfuric acid, which is actually it's just 0.011 or 1.1 times 10 to the minus 2. Right? Yeah, 1.1 times 10 to the minus 2. If you look at this Ka, is this fairly large or kind of small? What do you think? It's kind of big. It's kind of when we look at it, if we go back into the room and look at the chart in the room, at the border between strong acid and weak acid, tell me, do you know what's at the border between strong acid and weak acid? Like, in other words, what is the strongest weak acid on the chart in the room? The strongest weak acid on the chart in the room is oxalic acid. Oxalic acid's right at the border. After oxalic, then we go to strong. Do you know what the Ka for oxalic acid is? The Ka for oxalic acid is 10 to the minus 2. This is an unusually strong weak acid, trichloroacetic acid. In fact, some people call trichloroacetic pretty strong because hydrolyzed. And so HSO4 minus is right there near the border between weak acid and strong acid. HSO4 minus is a pretty strong weak acid. How do I know it's a pretty strong weak acid? I know it's a pretty strong weak acid because it's got a Ka of about 10 to the minus 2. Now, if this is a pretty strong weak acid, then I'm going to start to worry about it. However, if this were pretty weak, let's say step 2 was 10 to the minus 4. If step 2 was 10 to the minus 4, I probably would skip it in doing pH calculations because, like we saw in that earlier calculation, I forgot what it was, but we saw that we barely got any additional hydronium. But in this case, we are going to get some significant additional hydronium. Now, this is going to the HSO4 minus that we form in step 1 is going to start step 2 here. And so we'll take this, but we also have what we call common ion. This common ion is going to affect how much hydrolysis we expect. We expect less hydrolysis with a common ion. This is a Le Chatelier's type principle. And so that's why we can't put this at 0 here, otherwise that could screw things up. And so this is going to be minus X plus X molar and plus x molar here. And so we'll have 0.10 minus x molar, 0.10 plus x molar, and x molar here. All right, so let's figure out what x is in this case. So Ka2 is going to be the hydronium ion concentration at equilibrium times the sulfate ion concentration at equilibrium divided by the HSO4 minus concentration at equilibrium. So we have that. If the simplifying assumption does work here, it greatly simplifies this problem, but we'll look at that in just a second. 0.10 plus x times x divided by 0.10 minus x. So let's try the simplifying assumption. That means 0.10 plus x is just going to be 0.10, and 0.10 minus x will be 0.10. So if we add a drop or lose a drop of water, it doesn't really change anything here. However, x, we can't drop that because that's significant compared to 0. And so in other words, x is equal to Ka2. And so that's going to be 0.011. Now, if we look at the percent change here, what is the percent change? Well, the percent change is going to be 0.011 over 0.100, which is 11% change. 11% change, is that acceptable? No. Unfortunately, the simplifying assumption failed here because the percent change is too big. And so we're going to have to solve this using quadratic. So let's go ahead and get it into quadratic form. And so if we solve this, this is going to be 0.1 times 0.011, which will be 0.0011, and then minus 0.011x. I took it out of scientific notation just to make it quicker, plus 0.10x plus x squared. All right, so let's combine the terms here. So I'll get x squared plus 0.111x minus 0.0011 is equal to 0. All right, does somebody have a calculator? They can just punch in the A, the B, the C here. Let's get this. Okay, so x is equal to 0.00915. Thanks. Thanks. Yeah, so it wasn't 11%. It's more like a 9% change here. And so let's go ahead and calculate it. So what we'll have here is about 9% hydrolysis. Yes, it is definitely a weak acid. It's not a strong acid where we get 100% hydrolysis. It's a weak acid, but it's a stronger weak acid. But even a stronger weak acid, you look at this, is still only 9% hydrolysis. And so here we're going to get 0.100, let's say, minus 0.00915. This is going to give me 0.09085 molar. And then over here we got 0.10 plus x, so this is equal to 0.10 plus 0.00915, which will give us 0.10915 molar. Is that right? And then the sulfate is going to just be 0.00915. 0.00915. All right, let's double check this just to make sure. Looks okay. And so the double check, we'll just take this times this divided by that. So 0.10915 times 0.00915 divided by 0.09085. And I get a K, on the double check I get a K equal to 0.01099. So if I look at it, it's supposed to be 0.011. I got 0.01099. Let's just round off here. It's close. And so this looks good. So I double check this. But here even though it might not look like it, I went from 0.10 to about 0.11. So I added about 10% hydronium. If I add about 10% hydronium in step 2, that means the hydronium ion concentration increased. Therefore, will that negatively impact step 1's equilibrium? In other words, did I perturb this by Le Chatelier's principle? If I increase the product concentration, this one should shift left and I'm in an endless loop. Is that the case for this problem? No. We're safe here because this is a one-way reaction. When we have a Ka that's very large, it just goes one direction. In fact, the attraction between the hydronium and the bisulfate here is so weak, that's what makes a strong acid strong. It doesn't really react. And so I could dump more of this in, or I could dump more of this in, and I'm not going to get much reverse reaction to take place. Of course, the probability of reverse collisions increases, but as does the probability of forward. Well, and so in this case, here, step 2 was important. In most cases, the Ka for step 2 is going to be much smaller, like 10 to the minus 5, 10 to the minus 6, 10 to the minus 7. If you see something like that, what you'll notice is there's barely any addition. Let's go on to, let me erase this here, space here. Let's go on to step 3, because there are 2 types of calculation. One is pH, one is inventory. And so we'll do this as an inventory problem as well. And so if we want inventory, we need one more hydronium ion producer, and what would that be? And so in step 3, we would do Kw, the remaining. Because here, sulfate's not going to produce any hydronium. So that's the end of the line there. So the only other hydronium ion producer would be H2O and H2O, which gives us some hydronium and hydroxide. All right. Now this is going to be a common ion problem too. All 3 of these steps have the common ion hydronium, and so we've got to make sure that that's there. And so we're going to carry this down. And so far from step 1 we got 0.10. From step 2 we got an additional about 10%. Let's see how much we get from step 3. So this is going to be 0.10915. This is a running total. And so this is my running total, and this running total has to satisfy all 3 equilibria, which so far it does. So let's see. Initial water is a pure liquid. So admit that. And so this is going to be plus X molar, and then at equilibrium 0.10915 plus X molar, and then X molar. And so Kw is going to be the hydronium times the hydroxide. So this is going to be 0.10915 plus X times X. Now, because the Kw here is so small, 1.0 times 10 to the minus 14, I really don't expect much hydronium additional, especially with a common ion effect like this. This is a common ion effect inhibits the forward reaction there. So I really, in fact, what's the most hydronium? If there's no common ion effect there, how much hydronium would I generate? If both of these were 0, the amount of hydronium I'm going to generate would be, give me a number. If there was no common ion here, and this was 0 and 0, what is the most hydronium I'm going to get at 25 degrees C?
Square root of 1 times 10 to the minus 14.
Which is
1 times 10 to the minus 7.
1 times 10 to the minus 7. So the most I'm going to get is 10 to the minus 7 molar, right? The most. The absolute most I'll get from here is 10 to the minus 7 molar hydronium. But now, because of the common ion effect, I expect to get a lot less. Well, what's a lot less than 10 to the minus 7? Well, 10 to the minus 8, 10 to the minus 9, 10 to the minus 10 molar. Now, if we think about that, would 10 to the minus 7, or actually 10 to the minus 7 is the most, would 10 to the minus 8, 10 to the minus 9, 10 to the minus 10 molar add much additional hydronium to this? That's like 7 zeros, 8 zeros, 9 zeros. And then, no, it's barely going to add anything. But if we're doing inventory, we got to figure out all of them. You know, if we're doing pH, there's no reason to do this step because we would get so little. But we could do it, you know, just to be certain. And so here, what I'll do is I'm just going to go ahead and use the SA, the simplifying assumption. You know, a simplifying assumption I'd expect to work because K is quite small, and this is kind of the significant concentration here. So this is going to be 0.10915 plus X will just give us 0.10915 times X. And so X is equal to 1 times 10 to the minus 14 divided by 0.10915. 1 times 10 to the negative 14 divided by 0.10915. And so I get 9.16 times 10 to the minus 14. And so it wasn't even close to 10 to the minus 7. 9.16 times 10 to the minus 14 means this. This is 0.10915 plus point. Now I have to add 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then a 916. And so I'm going to get 0.10915, 3, 6, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, and then a 916. Did I add much to it? No, this is really negligible. And in fact, the percent change is going to be, you know, if I look at the percent change, we could just do order of magnitude here because it's so small. But, you know, the change is like 10 to the minus 14, possibly 10 to the minus 13. And then the original is 10 to the minus 1 times 10 squared. You know, it's going to be roughly 10 to the minus 11% change. Well, 10 to the minus 11% change is minuscule. And so the hydroxide ion concentration is going to be 9.16 times 10 to the minus 14. And then we should double check this. Let's go ahead and double check. When we double check this, let's say this times 0.10915. I'm not even going to bother punching in all these other numbers because my calculator's not even going to take them anyway. And it comes out to 1.00 times 10 to the minus 14. And so the double check is good. Did this step 3 perturb step 2? What do you think? I mean, yes, in a way it did, but look how little the change is. So essentially it didn't. You know? And so in other words, step 3 and step 2 will have the same equilibrium. I mean, well, and that would be the final here. So if I take this final and put it back into here and double check it, it's going to come out the same. So we're good. This is all good. And so in this case, yes, for sure, there's a huge change going from step 1 to step 2. A huge change in hydronium should upset step 1, but it didn't because step 1 is a strong acid. And we got lucky here because going from step 2 to step 3, there was a minuscule change, which a minuscule change is not going to upset the equilibrium here. And so we're good here. Therefore, if we're unlucky, we have to use what method to solve this? That is, if one of these steps perturbed the previous step, we would have to use what method? There are two methods. There's this method, stepwise. Stepwise isn't correct. You know, the correct method is to solve all these by using the other method, simultaneous. What we're doing here is we're just saying, okay, stepwise isn't correct because really we have to solve these simultaneously for all the common ions have to have an equilibrium concentration the same. And the only way to get that is, you know, exactly the same. The only way to get that is doing it, you know, simultaneously. But this is so close, you know, that it's acceptable. And so what we do is we simplify it by doing it stepwise. You know? But in reality, we shouldn't. We should do it simultaneously. But the math in simultaneous is too difficult, and therefore stepwise is the preferred method for solving this. And so if I have a solution that's marked, if I have a solution that's marked 0.10 molar H2SO4, what all is in there? And so if I look at the H2SO4, the molecule concentration, the H2SO4 concentration is 0 molar. There shouldn't be any molecules intact. In fact, all the molecules should have reacted with water and hydrolyzed to form hydronium and bisulfate. And so the H2SO4 is 0. So this is the final concentration of H2SO4. Now the hydronium continues. So in the first step we generate 0.10. In the second step we add a little bit to that, about 10%. In the third step we don't really change it. And so this is the final cumulative, this is the total running concentration of the hydronium here. And so the hydronium concentration will be a hair above 0.10915. Well, we'll just say 0.109 molar. Just slightly above 0.109 molar, or 0.11 molar, rounded to the proper number of sig figs. Okay, the bisulfate, we follow that along. In the first step, we generate this much. In the second step, we lose a little bit. And this is where it ends. And so the bisulfate, the running total, ends here, which gives us, for bisulfate ion, concentration of 0.0908 molar, or about 0.091 molar. Okay, and then sulfate stops here. So this is the last. We don't add or subtract in subsequent steps. So sulfate is just going to stop there at 0.00915 molar, or 0.0092 molar, rounded. And then we already got the hydronium. We have the hydroxide here. This is the end of the line for the hydroxide. In acid solution, the hydronium has to be bigger than the hydroxide, which is the case. The hydroxide is very small, 9.16 times 10 to the minus 14 molar, or 9.2 molar. And so this would be the inventory. Now, the pH we get from the total hydronium. And the total hydronium is the hydronium from all three steps, and that would be the final amount here. And so we just take the negative log of this. 0.10915. The pH is 0.96. Actually, how many sig figs are we allowed? Just two. 0.961 pH here. If we stopped at step 1, we would have gotten a pH of 1, but it's slightly more acidic. It's 0.96 rather than pH of 1. That's because of step 2. If we carried on to step 3, it wouldn't have changed. In fact, our calculator wouldn't have been able to handle that minuscule change anyway. All right, so this is what happens. For like a polyprotic acid. And what we do is stepwise works good if there's a big difference in the Ks. Like, so for example, K1 to K2 is like 10 to the third or bigger, then it works very well. Then at least another 10 to the third here. Now, if the K1 going to K2, the Ks are very close. Let's say K1 is 10 to the minus 5, K2 is 10 to the minus 6, then we have the risk of simultaneous, because both steps will generate significant hydronium. And so let's look at a little bit more complex mixture. It's more complex. More complex would be like an acid. Acid 1 plus acid 2 You know, if we have acid 1 and acid 2 in solution, then well, we look at this. We look at Ka for acid 1, Ka for acid 2. You know? And so we just do it in the same manner. We just start off with the biggest K. And so an example of this would be like HCl and acetic acid. If we have an HCl acetic acid mixture, then we look for the hydronium ion contributors to this. And so if we have an HCl acetic acid mixture, what are the hydronium ion contributors? Well, HCl, acetic acid, and water. And then we would just start off with the biggest K. What's the biggest K here? HCl. And so that would be like step 1 here. You know, this is a strong acid. And then we have acetic acid. Well, acetic acid is a weak acid. That would be step 2 here. But this step 2 would have a common ion. That would be hydronium. And so that helps prevent as much hydrolysis as acetic acid would have in pure solution. And then there's going to be no perturbation because, you know, HCl will be, you know, even though acetic acid might generate. Or we could have 2 weak acids. If we have 2 weak acids, then we run the risk of having to do it simultaneously. But it depends on the strength difference. If we have 2 weak acids and the K difference is 10 to the third or greater, then we can do it stepwise. If we have 2 weak acids and the Ks are kind of similar, then maybe it's going to be simultaneous. We have to check it. But we always do these things stepwise first. And so this will be like an acid mixture. It could be strong acid, weak acid. It could be strong and strong. If we have 2 strong acids, then it doesn't matter. You know, you just pick one and then do that as step 1, pick in step 2, and then just add however much hydronium step 2 gives. So 2 strong acids is pretty simple. A strong and weak acid, well, this is kind of what we did here. And 2 weak acids, potentially complicated. All right, the same thing happens with mixtures of bases. You know, we just look at it. Let's say if I add acid 3, acid 4, acid 5, we just keep adding additional steps to it because we have more hydronium contributors. And so we just have a mixture of acids. All right, in chapter 17, what we're looking at, and I just need to touch on this for today's lab, is this. In chapter 17, in chapter 16, we had acid and water, and we had base and water. Those were kind of acid-base mixtures because water is either an acid or base. So if I have acid and water, acid acts as the acid, water acts as the base. And so that's an acid-base mixture. In chapter 16, if I have base, the base is the base, and water is the acid. And so this is acid-base mixture. Well, chapter 17 is looking at a little bit more complicated acid-base mixtures. You know, where, you know, we would have, let's say, a stronger base than water. And so in chapter 17, our strategy is typically like this. In chapter 17, we mix we always react the strongest acid plus the strongest base present. And so whenever we have an acid-base mixture, that's what we're going to do. It's the first step. We take the strongest acid present and mix it with the strongest base. The strongest acid present might not be a strong acid. It could be a weak acid, but it would just be the strongest of all that are present. And so we have lots of different types of mixtures like this. But I would divide it a little differently than your book. I'm going to follow your book initially. Your book is going to come out with a acid plus a salt type mixture and a base plus salt. The acid plus a salt mixture, you know, this is what it's going to look like. Let me give you an example here. Let's take HCl and a sodium chloride. And so here I could have an HCl acetic acid, but here I'm going to have HCl and sodium chloride. So how do I handle this type of mixture? If I have an HCl and sodium chloride mixture, the way we'd handle it is we start off with the biggest Ks, you know, first. Well, the biggest Ks, we know that, you know, sodium chloride is a strong electrolyte. Sodium chloride, automatically, we should know that this is going to consist of sodium ions and chloride ions. So we take the strongest acid present. What's the strongest acid present? HCl. And so we'll take the strongest acid present and react it with the strongest base present. What's the strongest base? Well, sodium ions are neutral. Chloride is too weak, right, to hydrolyze water. Therefore, the strongest acid present is HCl. The strongest base present is what? It's not chloride. The strongest base present would be water. And so the first step is going to be the strongest acid present plus the strongest base present. Well, that just looks like Ka for HCl, and it is. And we have something like this. And so if we put in some concentrations here, let's say this is 0.1 molar, this is 0.1 molar. 0.1 molar is a very popular concentration. The reason 0.1 molar, you think 0.1 molar is really dilute, isn't it? You know, most of the time we're working with 3 molar, 6 molar, this kind of stuff. But 0.1 molar is not very concentrated at all. But the reason we use 0.1 molar all the time is because we need these to be dilute, because the more concentrated these solutions become, the more concentrated these solutions become, the more we have to worry about what?
Reduction in activity.
Yeah. The more we have to worry that the stoichiometric concentration is going to deviate more and more from the effective or real concentration. And so this is like ideal gas. You know, when you're using the ideal gas law, you like to keep the pressures and the temperatures within a certain range. You know, because if the pressures start to go extremely high, the ideal gas law is going to fail. Well, the same thing here. If the concentrations start to get too high, then our assumption that the activity is equal or to the molar concentration, stoichiometric concentration, is going to be farther off. And so 0.10, you know, this is why pHs from 0 to 14 are okay, because we can say that those kind of behave ideally. But once we get to much lower pHs and much higher pHs, lower than 0 and higher than 14, then it's going to deviate from the stoichiometric concentration. We really have to use activities for that. And it's not, you know, it's not a linear type effect with that. But anyway, let's go back to this here. So we just picked the strongest acid. Well, the strongest acid present is HCl. We know we have 0.10 molar. Water is a pure liquid. Hydronium, we just say nothing's happened. But here, take a look at chloride. We're starting off with not 0 chloride. We have some chloride present. We have some chloride present from sodium chloride, and that's going to be 0.10 molar. And so when we have an acid plus salt or base plus salt, if there's a common ion between these two, you know, then they're going to impact each other. And these type of problems are called common ion problems. If there's no common ion, then we just treat them separately, you know, like a chapter 15 or something like that. And if the salt is totally unrelated to the acid, then the salt's not going to have any impact. We can just largely ignore it. Or we have to look at it because it could hydrolyze water. But in this case, this is. And so, you know, but I already know K for this is very large. So, but if I took a weak acid, let's say a weak acid like acetic acid. If I take acetic acid and I put in some sodium acetate, then I'm going to have a different type of scenario come up. And so we'll look at that also. That different type of scenario is this. You know, the salts can be neutral, salts like sodium chloride. Sodium chloride we call a neutral. Sodium nitrate's a neutral salt. But salts can also be acidic or basic. You know, like ammonium chloride is acidic. Sodium carbonate is basic. And so we got a neutral and basic salt. And so this is a little bit more complicated here. And so what we're going to do is we're going to look at these more complicated acid-base mixtures. So the first part of this would be 17.1. In 17.2, we're going to look at buffers. But before we get to buffers, we'll look at other mixtures. And so if we have a strong acid, strong base, a strong acid, strong base mixture we call, titration, like it, sodium hydroxide and HCl, like HCl and sodium hydroxide. And we've done these. This is like Chem 1A. We could do a Chem 1B style ice table for this as well, or 1B ice table. And so in Chem 1A, you'd have something like this is no problem. Now, what if we have something like a strong acid and a weak base? And so let's say we take HCl and a weak base would be something like sodium acetate. Sodium ions are neutral, and so sodium acetate is a soluble salt, so it's going to consist of sodium ions and acetate ions. Acetate ions are weak base, and so if we have this HCl and acetate would be the reaction here. And so the other mixtures would be like this, or we could have a strong acid and water. Let's just add that in here. Strong acid and water, well, that's chapter 16. It's chapter 16. This would be chapter, well, actually, this is Chem 1A too. Chem 1A or 1B. The reason why these, like Chem 1A style problems, is because of this. The most likely reaction would be with the strongest acid present. Let's go back to here. Strongest acid present is HCl, strongest base present is sodium hydroxide. What forms here? HCl and sodium hydroxide is going to produce what? HCl and sodium hydroxide produces NaCl and H2O. What is K for this reaction?
Very large.
Well, I don't call it very large. You know what I call it? I call this one very, very, very large. Why do I call that one very, very, very large? The reason I call this one very, very, very large is because very, very large I have reserved for this. If I take HCl and react it with a weaker base, the driving force is going to be smaller. If I take HCl and react with a stronger base, the driving force is a little bit bigger. Actually, I'll do it complete, sorry, with sodium acetate. I'm going to get, what am I going to get? I'm going to get acetic acid and sodium chloride. Acetic acid and sodium chloride. And so the K for this one is going to equal very, very large. Because I reserve very large for what? Very large is reserved for HCl and water. HCl and water is going to produce hydronium and chloride. And we already know K for this because you're supposed to have memorized it. The K for this is very large. And so this is the way we go. Water, how strong of a base is it? Not strong. Acetic acetate, a stronger base. Sodium hydroxide is a strong base. And so the driving force is going to go up. If the driving force goes up, then this is the way it's going to be ranked. It's going to be ranked very large, very, very large, strong acid, weak base, and very, very, very large for strong acid, strong base. Does that make sense? And so this is ranking. And so these we could easily do with Chem 1A. We just look at the limiting reagent, this type of stuff. The Chem 1B part comes here. For something like this you do in Chem 1A, we can figure out the pH of this. The pH is going to be 7, assuming it's stoichiometric. Because if we have stoichiometric quantities of both of these, we're just going to get salt water. This salt, sodium ions are neutral, chloride is too weak, and therefore a pH 7. This one is more appropriately done in Chem 1B, but you've done these in Chem 1A. You know, you've done them just for stoichiometry, but you haven't done them for pH. For pH, this one's a little more tricky because if we have stoichiometric quantities of HCl and sodium acetate, then there's going to be a step 2 because we're going to form acetic acid. If we form acetic acid is a lower pH, so the pH is going to be less than 7 here. And we got to add on a step 2 because we got to figure out how much hydronium is going to be produced. So there's going to be, once these have neutralized each other, we're left with acetic acid. Sodium chloride's neutral, so it's acetic acid and water would be step 2. And then we can figure out the pH. So we got Ka for acetic acid followed by Kw. And so we might have to do a Kw, but chances are not because Kw is so small in determining a pH. Okay. And so likewise, we could have the reverse. Weak acids reacting with a strong base, a weak base and water. Oh, actually, no, let me do that again. Strong bases are pretty simple mixtures. If we got a strong base, we could react it with a strong acid. Well, we just did that. Strong base and strong acids is the first one. Just flip it around. We could have a strong base reacting with a weak acid. And so a strong base, what would be a strong base? A strong base would be something like sodium hydroxide. A weak acid would be like acetic acid. C2, H3O2. What would K for this reaction be? Or we could have a strong base plus water. We have a strong base like water, like say, oh, I got sodium hydroxide plus water. What would K for that be? And so this is like we were saying before. This one we recognize because you know what reaction this is. Strong base and water is called K. What? KB. And what is the KB for strong bases? Very large. Very large. And so we have a strong base plus water. Well, water is not a great acid. If we increase the strength of the acid, we increase the driving force. And so this K should be very, very large. Good, catching on there. And this K we already know because we just said it. This one's going to be very, very, very large. So this guy. So it turns out whenever we have a strong base or strong acid, this is the summary. The take-home point is strong acids and strong bases react to completion. They're always going to react to completion because the worst acid or worst base is going to be water, and it's still going to react to completion with water. Although we could have an even weaker, but you know all these are aqueous solutions, so it'd be the worst potential. Now the complication comes here, and that's what we're going to talk about now. What happens when we have a weak acid and a weak base? What's K for that? And so let's take a weak acid plus weak base.
K is small.
K is small. Yeah, K is small. Is it very small? No, it's just small. I don't know what it's going to be. So when we have a weak acid plus a weak acid, things start to get much more difficult of the weak acid. Let's take an example here. An example would be, let's take acetic acid and let's take ammonia. Acetic acid. Although these are decent, they're still weak. And so acetic acid plus ammonia, that's going to give us acetate and ammonium. Oops. So what is the K value for this? Well, tell me all the ways we can determine what K is. Can I look this up in the table? It's not in the table. Let's take a look at appendix D again. Do I know the K value for this reaction? Because I know it's not going to be very large or very, very large or very, very, very large. Let's see. That's a K value for this one. You can solve the item table. So let's take a closer look at appendix D here. We got table D3. Table D3 is the Kas for weak acids. Ks are also called ionization constants, or hydrolysis. But I got a chart of Kas, and I told you we have to calculate the Kbs, but we don't have to calculate the Kbs for everything. You know, you know what these class of compounds are called? Aniline, codeine, diethylamine, dimethylamine, ethylamine, hydrazine. What?
Is it amines?
Amines, right. Amines are ammonia-like organic compounds, and they're ammonia-like organic compounds because, you know, rather than having another hydrogen there, we got two hydrogens, we got a carbon bonded to it. Well, carbon and hydrogen have approximately the same, or roughly the same electronegativity, so it doesn't change the basicity of the nitrogen much. And so these are amines. And so amines are a class of bases. And let's take a look at some amines here, really briefly, to see what we got going. And so we know ammonia is a decent base. Ammonia has an electron pair, can donate. We've got a delta minus charge on that. And so what happens if we replace it, we replace it with what's called a methyl group here? You know, is it still going to act as a base? And the answer is yes, because, you know, hydrogen is 2.1 electronegativity, carbon's at 2.5. And so it doesn't really change the electron cloud around nitrogen. So this is just like a base like ammonia. So the basicity of methylamine and ammonia are going to be very close to each other. And so we don't have to replace it with a methyl. We could replace it with an ethyl. We could replace it with a propyl. We could replace it with a whole bunch of things and still get that base characteristic. A lot of these amines are drugs, like morphine is a drug, etc. And so this is the organic class of amines. And these are very common basics. What do you think would be more basic, ammonia or methylamine? What do you think would be more basic, ammonia or methylamine? Without looking at the chart. Not look at the chart. You tell me, based on structure, what's going to be more basic. They're going to be about the same, but which one will be slightly more basic and why? Ammonia, and why? Why would ammonia be more basic?
It has stronger dipole.
Okay. It has a stronger, what, you know, a stronger dipole means more basic? The bigger the dipole, the more basic it is? Can we make a law, the law of the dipole, and just calculate the strength of the dipole, or measure the dipole and then measure its basicity? I mean, in what way does a dipole impact it? Yeah, you would expect, maybe you would expect this to have a stronger dipole. And because you're looking at the electronegativity difference, right? And so rather than saying stronger dipole, you phrase it in terms of negative charge density on nitrogen. A bigger dipole means a greater negative charge density on nitrogen. More negative charge means a better base, right? Like we talked about the other day, we want to localize. If you want a strong base, you want to localize the negative charge. You don't want to delocalize or spread it out. And so one thing you might say is this. You might say, hey, you know, hydrogen and carbon are not exactly the same electronegativity. In fact, what has a bigger electronegativity? Well, nitrogen's the same in both of these. The difference would be hydrogen and carbon. Which one would have a greater electronegativity? Carbon's a 2.5. Well, if carbon's a 2.5 and hydrogen's a 2.1, that means carbon will suck more electron density away from nitrogen. If carbon sucks more electron density away from nitrogen, it makes nitrogen less negative. In other words, it delocalizes some of the negative charge density on, and when we were talking about localization versus delocalization, we're looking at charge. You know, all these chemical reactions, you have to think in terms of charge and charge interactions. And so here, that should make this delta minus smaller because this is more electronegative, right? And make it less basic, you know, less attracted to protons, you know? Is that correct? Is that correct? Well, let's take a look at the numbers, you know, because whatever we say has to agree with the numbers. And so let's take a look at the numbers and then see the difference. Ammonia has a kV of 1.8 times 10 to the minus 5. Methylamine has a kV of 4.2 times 10 to the minus 4. And so 10 to the minus 5 versus 10 to the minus 4, which one's going to produce more hydroxide? This is kV's base hydrolysis producing more hydroxide. Which one will produce more hydroxide, methylamine or ammonia? Methylamine or ammonia? Well, okay, think in terms of acids. The bigger the K, the stronger the acid or the weaker the acid? Like, for example, strong acids have a big K or a small k? Strong acids. KW, I mean not KW, Ka. What's the Ka for HCl? Very large. Is that big or? That's big, right? That's big K. So the bigger the K, the stronger. The bigger the Kb, the stronger. And so this tells me that which one's a stronger base? Ammonia or methylamine? Methylamine's stronger. But hey, wait a minute, didn't I just say the opposite? Didn't I say because of the inductive effect, the greater electronegativity on carbon is going to suck electron density away from nitrogen? Didn't I just say that? Yeah. And so what I just said is wrong. It can't be right because methylamine is stronger. So why is methylamine stronger? Methylamine is a stronger base. It's 10 times stronger than ammonia. Why? Well, is it 10 times? It's awfully, yeah, it's more than 10 times stronger. It's more than 10 times stronger than ammonia. Shoot. I can't use that.
Intermolecular forces?
No. Intermolecular forces will come at play, but that's not the reason why. Intermolecular forces is the reason why HF, you know, the interionic attractions, ion pairing. But
Doesn't ammonia also form hydrogen bonds?
it does, but both of these form hydrogen bonds. So what's the difference?
Well, I thought ammonia might form a stronger hydrogen.
Well, ammonia was going to form more hydrogen bonding. It's going to have greater hydrogen bonding interactions than this. But will that account for tenfold difference? More than tenfold? Okay, so I form a little less efficient hydrogen bonding because the methyl group, you know, is a little bit bigger. Will that account for tenfold difference? No, it's not. Like, for example, because the hydrogen bonds are tenfold times greater, it's going to have 10 times the boiling point. But the thing is, you know, I'm using electronegativities to I should have looked this up earlier. You know, what kind of electronegativities are we looking at? What are they called? They're called Pauling's electronegativities. And the Pauling's electronegativities, how accurate are those? How accurate are those? In other words, if we want to dig deeper into this, it's very simple, actually. I would have predicted methylamine to be a stronger base. Why would I have predicted methylamine to be a stronger base? Because I know methyl. I know methyl. Is methyl electron rich or electron poor? Is methyl electron rich or electron poor? When I ask you questions about electron rich or electron poor, what should you do first? Or you probably haven't done enough of these then. You need to do more of these because hydrocarbons or electron methane. Is methane electron rich or electron poor? Well, you know, yeah, it's electron rich. Methane's a great fuel, burns. You know, there's certain things you should have, like basic knowledge, like memorize this type of stuff. But hydrocarbons are all electron rich.
The methylene is the fact that the nitrogen has a different oxidation state.
No, the oxidation state in nitrogen's the same in both of these.
Who's the bond between nitrogen and carbon covalent?
The bond between nitrogen and carbon is covalent.
So that's
But what degree? Do you guys remember percent covalent, percent ionic character? Percent covalent, percent ionic character from. Do you guys remember this chart from chapter 10? Can you give me a one-sentence synopsis or summary of this chart? From this is Figure 10-7. Even though the oxidation states aren't accurate, they tell us. They tell us a lot of information as far as limits go. And so, yeah, it's not totally accurate because it is covalently bonded, but still, it tells us information about the extremes. Now, here, nitrogen is the same. Nitrogen is -3 in both of these. The difference is this. The reason why methyl, and this is, in organic chemistry, we call these electron pushers. Electron pushers are things that are electron rich, and they can push electron cloud density to whatever they're attached to. This methyl is called a substituent in organic chemistry, and we have electron withdrawing substituents, which are electron poor, and that changes the character of the nitrogen, versus electron pushing substituents, which are electron rich. Methyl is an electron pusher because what's the oxidation state on carbon? -3. 2, 4, 6. Close. -2. On this carbon, it's a -2, which means that this is electron pusher. Electron pusher. However, if this were like this, let's say I had something like this attached. This carbon, hey, this carbon has the same electronegativity, doesn't it? And so delta En is the same. And so the percent ionic character, the percent polarity is the same. No, it's not. It's not the same because this carbon is very different than this carbon. This carbon would be an electron sucker or electron withdrawer because this carbon is what? It's the oxidation state on that carbon. +4. Good. This is a +4. Totally different. This is not an amine. This is not even very basic. This would be much more acidic than basic.
So even though in the nitrogen carbon bond, the nitrogen takes the electrons, we still call it.
Yeah, it does, but nitrogen's still more electronegative, but now the tug of war has a totally different dynamic. Before, here, nitrogen, no problem, pulls the electron cloud towards itself. Here, it's still going to pull the electron. In fact, this carbon's so electron rich, it says, okay, there's even more, let's say, electron cloud. You take it, nitrogen, right? But in this case, it's a different scenario. This carbon is starving for electron density. And so now it's not going to be so generous. This carbon's very generous. This carbon is not going to be generous. Why? Because it doesn't have much to give. You know, it's like, okay, I'd like a donation of electron density. Well, the carbon's broke. It doesn't have any electron density. It can donate, does it? Or it's already given it to nitrogen. Nitrogen wants more. But this carbon's broke. Can it give more? This carbon's rich. It can give a lot. And so this is not what we call an amine. So for example, let's do this. Let's say I replace the hydrogens with fluorines. What's going to happen to my Kb? Will my Kb go up? That is this going to be a stronger base than ammonia, or will my Kb go down? It's going to go way down. This isn't even an amine. We don't call this an amine. Amines are when we have carbon or hydrogen bonded to the nitrogen, but we have to be careful about the carbon, the type of carbon. This type of carbon is not going to make an amine. This stuff is not basic. This is basic, this is basic, this is not basic. This is not part of the amines. Because fluorines are electron withdrawers. Fluorines are going to suck the electron density away from nitrogen. And in fact, look at the oxidation state. The oxidation state of nitrogen, -3. The oxidation state of nitrogen, +3. Totally different dynamic here in terms of base strength. But anyway, I just took this slight tangent because I'm thinking about acid-base strength for organic chemistry, since I got complaints that the students needed some more help with that. So I want to talk about this. We're actually going to do, I actually had to skip a lab, but we're going to come back to that lab. We're going to do with the Spartans Acids lab. And the Spartans Acid lab is we're going to use quantum mechanics, a quantum mechanic computational program to look at acid strength and structure. And so we're going to come back to that later. So we'll talk more about acid-base strength later. So let's go back to the original question. The original question is, what's the K for this? And so this will be chapter 15. Tell me all the ways you can generate K. All the ways you can determine the K for a reaction. We could use delta G to figure out. That's good. Actually, let me write the reaction over here. We could use delta G to figure it out as long as we have these species. So we got HC2H3O2 plus ammonia. This is going to give us acetate and ammonium. And so we want the K value for this reaction. The K at 25 degrees C in under standard conditions will just be E to the minus delta G naught over RT. So we just figure out what delta G naught for this reaction is, and we can calculate the K value for this particular reaction. Once we get the K value, then we can do the ice table, right? Are there other ways of getting delta G? Yes, you got to know other ways. Otherwise, if there's only one way you can do it and I don't give you the data, let's say I don't give you the appendix D data for this, then you can't do it, right? And so is there another way we could figure out the K for this unknown? Well, it's a known reaction, but unknown, that is, we don't have it. This is chapter 15. If you think back to chapter 15, what are all the ways you determine K for reactions? Let's say you didn't have a K value for that. What are all the ways you determine K for reactions? So we could do this, just look it up in appendix D, but is there another way? Yeah, there is. It's the way we're going to do because I don't want to go back to table D2 or whatever it was. We'll run another time. So I'll just let me just tell you the other way. The other way is Hess's law. But the Hess's law type scenario where we add up the equations and multiply the K's is only valid if I have equations. But do I have any equations for this? I don't, but I do. I don't have them given to you, but you should know some equations. What equations do you know? If I gave you this table, because this table is relevant to this chapter, hey, I have this. I know a K value here. I have the KB for ammonia. But what can I do with that? This is a KB for ammonia. What's the equation for the KB for ammonia? Do you know? The equation for KB for ammonia, I know that because if I have this data, ammonia, KB is ammonia plus what? Ammonia plus water. So it's ammonia plus water gives us what? Yeah, ammonium and hydroxide. And that is going to have a KB of 1.8 times 10 to the minus 5. And then, you know what? I saw acetic acid here. There's acetic acid near the top. Interestingly, you'll see something. Acetic acid has a Ka of 1.8. They aren't the same. They're just the same to 2 sig figs. But if we went beyond 2 sig figs, they'd be different. But they just so happen to be the same to 2 sig figs. So what is the Ka? Well, the Ka is acetic acid plus water. This is going to give us hydronium and acetate. This is Ka. Ka, again, just by coincidence, happens to be the same to 2 sig figs. What happens if we add these two up? Are we getting closer? Yeah, we're getting closer. But we're not there yet. What else do we have to get? What else do we have to add to this? I have my ammonia, I have my acetic acid, I have my ammonium, I have my acetate. But I have too much stuff in there. I got to get rid of the hydroxide and the hydronium and the two waters. How can I get rid of the hydroxide, hydronium, and two waters? Have you seen that before? Two waters forming a hydroxide and a hydronium is equal to what? Kw. And so what I want to do is I want to reverse Kw. And so I'm going to go hydronium plus hydroxide yields H2O liquid plus H2O liquid. If I reverse this, what do I do with the K value? I invert it. And so I'll invert the K, it'll be 1 over Kw. Now if I add these three equations up, what do I get? I get the equation that I want. And so the K here is going to just be Kb of ammonia times Ka for acetic acid divided by Kw. And you can get the number for that. Well, since I went off on that tangent, the acid-base strength, I'm going to make a long story very short. The long story is this. Once I get the K value for this, I can solve the ice table. Actually, let's get that K value for that. So it's going to be 1.8 times 10 to the minus 5 squared. 1.8 times 10 to the minus 5 squared. Divided by 1 times 10 to the minus 14. 32.4. 32.4. And so initially I had 0.10 molar, 0.10 molar, 0 molar, 0 molar. And so this is going to be minus x molar, plus x molar, plus x molar. And so I'm going to 0.10 minus x, 0.10 minus x, x, and x. So this is going to be equal to the acetate, which is x times the ammonium. Let's going to square that, divided by this, and this. So that's square. Oh, this is easy. I don't even have to do the quadratic. I could just square root both sides. Do you see that? So I'll take the square root of this side and take the square root of this. And if I do that, then I'm going to get that x over 0.10 minus x is equal to the square root of 32.4. So let's go ahead and punch that out. So let me take the square root of this first. 5.69. And then times it by 0.1. So I'm going to get x is equal to 0.569. Okay. Minus 5.69x. Then add that to both sides. So I'll get 6.69x is equal to 0.569. And x is equal to 0.0850. We didn't have to use the simplifying assumption, in fact, for this because the math was pretty easy. And so this is going to be minus 0.100 minus 0.0850. And so it looks like it's 85% reaction here, 15% unreacted. So this is 0.015, 0 molar. So 15% of the remains unreacted, 85% reacted. Actually, both of these are the same. So this is going to be 0.0150 molar. This is going to be 0.085. Molar in 0.0850 molar. All right. So hey, we were able to figure it out. Now what? Now I want the pH. I want the pH of this. What do I do? Next. What do you tell me how you were going to get the pH of this? Just take a couple minutes and then we'll stop there. Actually, we don't have enough time to do it thoroughly yet. If I ask you for the pH for this, what do we do? Do we just look for the hydronium ion producers? Do we look for the hydroxide ion producers? What do we do? And so the situation is this. To make a long story short, I'm going to cut it short here. When we have a weak acid and a weak base, we have trouble in calculating the pH. The reason we have trouble in calculating the pH is because we get a situation like this. We get a situation, and this is actually a good thing and it's a bad thing. It's a bad thing if we want to do calculations. It's a bad thing if we want to do calculations because of this. This is going to be a stable mixture. It's a stable mixture of weak acid and weak base. This hasn't completely neutralized each other. And not only that, this is weak acid and this is weak base. And so if you look at this mixture is a mixture of weak acid and weak base that hasn't completely neutralized one another. And a mixture of a weak acid and weak base, it's a stable mixture because K is not big. And it doesn't completely neutralize. Well, and so the situation is this. Weak acid, weak base mixtures are stable in the sense that they don't completely react and we end up with weak acid and weak base at the end. And so these are called buffer solutions. Buffer solutions are stable mixtures of acids and bases, weak acids and weak bases. We have different types of buffer solutions. We have a weak acid and weak base that are unrelated. And then sometimes we have a weak acid and weak base that are related. In fact, they're conjugates to one another. if we have a weak acid and a weak base that are unrelated, like this, then what turns out is this is simultaneous. We have to solve for the Ka, the Kb, and Kw simultaneously. We'd solve for the Ka of acetic acid and the Kb for ammonia. Or we'd solve for the Ka for ammonium and the Kb for acetate, because these are redundant. These are conjugates of one another, and so we'd solve for, we'd end up with the same thing. And we'd have to include Kw. And so this turns out to be a very challenging problem. However, if the weak acid and the weak base are conjugates, so for example, if I had something like this, that's my mixture, I have the weak acid, acetic acid, and the weak base, sodium acetate, then that's a whole different story. Because if the weak acid and the weak base are conjugates, then we have a special name for this. This is called a Henderson-Hasselbalch buffer. Henderson-Hasselbalch buffers are easy to do the calculation because they're related. When they're unrelated, then we have to use simultaneous methods. But both of these are buffer solutions, because acetic acids and acid, sodium acetate's a base. Will the acetic acid completely neutralize the sodium acetate? No. I mean, in that neutralization reaction, we're just going to form a sodium acetate and acetic acid, the same thing. And so this is a stable mixture of acid and base. This is the acid plus salt. This is a stable mixture of acid and base. They're not conjugates of one another. And so today we're going to look at buffers, some of the properties of buffers. So we'll make a buffer and then measure its properties. All right, so I'll stop here. We'll take a break, and then we'll do the lab together. The lab is going to be modified from what you have. We'll talk about that.